Hello everyone, today we'll talk about the problem maximum total importance of roads. We're given a graph represented as a list of edges. You want to assign numbers from 1 to n, every number once, to all the nodes in our graph, and in such a way that we maximize the sum of values of edges, where a value of an edge is just the sum of the values of both the nodes that this edge connects. So, assign values from 1 to n to every vertex, maximize the sum of endpoints over all the edges. Our final solution will in fact be a greedy solution, and if we come up with it immediately, then we can of course implement it. And if we don't come up with the greedy solution, it turns out that there are many standard techniques, many standard observations that we can use in problems like this that will also suggest that greedy might be the best way to go here. So here are those basic ideas in problems like this. So the first idea is called the handshake lemma. And it's just the simple observation that, for instance, if we have a group of people and some people shake hands, we can consider such a situation to be represented by a graph where we have an edge between two people that shake hands. Then the total number of times every person has shaken hands is always even. The sum of degrees of all the vertices is even. That's because every edge adds 1 to the degree of both one of its endpoints and the other endpoint. So at every point, every handshake increases the number of times a person has been given a handshake by 1. So this is also, for instance, if we want to consider the sum over all the vertices of adjacent edges to that vertex, so that would be the sum of degrees, because the sum of adjacent edges, the number of adjacent edges, is just the degree, is the same thing as the sum over edges, summing over vertices adjacent to those edges, which is of course also a general fact that we can do when we look at sums. If we are summing something in some order, then we can typically swap the order, and maybe after swapping that order, the solution will be simpler. So in the example of the handshake lemma, when we look at the number of times every person has shaken hands, and maybe we don't have much of an idea what this value is. However, if we, for every handshake, count the number of times that people have taken the handshake, well, of course, this is always 2 for every edge. And that means that this whole thing is even, and this whole thing is the same thing as this whole thing. However, the order of summation is changed. And in our problem, since we want to maximize the total importance of roads, we can, of course, for every road, take the sum of values of both its endpoints, as is presented in the problem, or we may go through all the values of our nodes, and for every node, we know how many edges will have their importance increased by the value that we assign to this node. And this is, of course, in a way, an application of a third idea, which is contribution. So when we are looking at some sums, then we might want to look at those sums divided as contributions of particular elements. So here, the sum of values of all the edges, we might look at, first of all, how much the first node contributes, the second node contributes, the third node contributes, and so on. And all of that should suggest to us that the greedy solution is feasible. Because when we have, so the greedy solution will be something like this. We have our vertices sorted by degree, so we have every vertex sorted from those that have the fewest edges to those that have the most edges. And we want to assign bigger values to those that have more edges. So this is exactly what we want to do. And of course, if we want to convince ourselves that this is the best solution, it should be quite intuitive, but we might think about the simple exchange argument. So if we have two nodes, and those two nodes have two values, and one node has greater degree than another, however, that node with the greater degree has smaller number assigned, we can literally just swap the numbers. And that means that for every edge in the node that had smaller degree, the importance would decrease by the differences between those two values. And for every node incident to the node with, so for every edge incident to the node with higher degree, the value will increase by that difference. So if the degree of the first vertex is higher, then the increase will be to our benefit. The total importance will increase, right? So if degree of u is smaller than degree of v, or maybe w, and if value of u is greater than value of w, then you can see that by swapping these values, we'll increase deg w times our result by the difference between the two, decrease by degree of u times the difference between the two, and since this degree is greater than this degree, the total change will be to our benefit. So the last part is how to implement it. First of all, we want the degrees of all the nodes. So we can use the same thing that we used yesterday. So we take the roads, we unpack them, we chain them, so we create essentially an iterator over all the vertices in every edge. We flatten the list of edges. We initialize a counter over those, so now we know how many times every node appears in that list, which is just the degrees of all the nodes. We take them, sort it by their degree in ascending order. And now we go through all the vertices and their degrees, and at the same time we go through all the possible values, and we assign those values greedily. And now what we want to think about is also the fact that maybe some nodes do not appear in the list of roads, because the graph doesn't have to be connected, but that just means that, well, we don't care about components, so we only care about degrees, not that some parts are disconnected. We just want not to forget that we have to add some values to nodes that do not have any incident edges, that have degree 0, and of course we want to assign as small values as possible to them. So we want to start not at 1, but start at the smallest number necessary. So we want to essentially skip over all the numbers that go to vertices that have degree 0. So here in our list degs, we have the list of all the non-zero degrees. So all the remaining vertices are n minus the length of that list. So we want to start at 1 plus that. So we skip over all the vertices of degree 0. And then we add to the result, because we want to return the maximum, the sum over all the edges of their values, the degree times the value. So the contribution of this vertex. And after all, we can just return the result.